We're going to look at the ideal gas law, which is PV equals nRT, this equation here. And as this little graphic shows, this first one is the pressure, the V is the volume, N for number of moles, R is the ideal gas constant, and that has several different values, and temperature has to be in Kelvin. We're going to try some of the problems that were on the revised version of this worksheet. So if we look at this, it says what's the pressure, so we're looking for a P of 1.2 moles of SO2 gas in 4-liter container at 30 degrees, and before we have a chance to forget, we're going to change that to 303 Kelvin. So the ideal gas law is PV equals nRT. We're looking for the pressure, so the pressure is nRT over V. And we're going to substitute some values in. 1.20 moles. Our R, okay, because we are using pressure, the value of the unit on the pressure depends on which R we're going to use. So we'll just use 0.0821. That's in liters, atmospheres per mole Kelvin. And that means our answer will be in atmospheres. The temperature here is 303 Kelvin. And this is all divided by V, which we said is 4 liters. Now if we go back and do all this calculation, we get 7.46 atmospheres. Problem 1. How many moles, that's N, will occupy a volume of 2.5 liters at 1.2 atmospheres and 298 Kelvin, which is our temperature. So we're looking for moles, so we're going to say that PV equals nRT, and N is equal to PV over RT. Pressure is 1.2 atmospheres. Volume 2.5 liters. R, because we're using atmospheres, the value of R 0.0821, and that's liter atmospheres per mole Kelvin. And the temperature is 298 Kelvin. When we go back and calculate that, we get 0.123 moles, and that's after we've rounded that off to 3 significant figures. Problem 2. In problem 3, it says what is the volume of 0.6 moles at 50 degrees. So 50 degrees is 323 Kelvin. We add 273. And the pressure is 600 torr. Now, because we're using torr now, we have a different value of R, and R is going to be 62.4 liters, millimeters of mercury, or liters torr per mole Kelvin. So again, we have PV equals nRT. Now we want the volume, so volume is nRT over P. So number of moles, 0.60 moles. R, we said, is 62.4 liters torr, or millimeters of mercury, per mole Kelvin. And the temperature is 323 Kelvin. All of that over the pressure of 600 torr. Now when we go back and calculate, we find out that comes out to be 20.2 liters. Problem 3. At what temperature, so this time we're looking for a temperature, will 1.80 moles occupy 4 liters at a pressure of 350 millimeters of mercury. So again, because we're getting 350 millimeters of mercury, we're going to use 62.4 as our value. Okay, PV equals nRT. We're looking for temperature, so temperature is equal to PV over nR. Pressure, 350 millimeters of mercury. Volume is 4 liters. The value of N, 1.8 moles. And our R, again, we said would be 62.4 liters, millimeters of mercury per mole Kelvin. Now we do the math on this, and we get a temperature of 12.5 Kelvin. Which is the rounded off version of the calculator answer. Now we might also want to say, okay, what would that be in Celsius? And if you subtract 273, that equals negative 261 degrees Celsius. So either answer would be correct. If the problem does not state do it in Celsius, give the answer in Celsius, then leaving it in Kelvin is fine. A balloon filled with helium has a volume of 1.3 liters at 15 degrees. So if it's 15 degrees, then we're going to change that to 288 Kelvin by adding 273. The pressure is 700 torr, so our value of R again is going to be 62.4. How many molecules? So we see this and go, oh, you know, if I knew the number of moles, I could change that into molecules. So we're going to have a step to do later. So we're going to say PV equals nRT. We're going to look for the number of moles. So N equals PV over RT. Pressure 700. Volume 1.3. R 62.4. And the temperature 288. Okay, we can do the calculation and find out that we get 0.0506 moles. And then we go back and do a separate problem. If we have 0.0506 moles, then we just use our conversion factor that 1 mole is 6.02 times 10 to the 23rd molecules for this gas. And we get a final answer of 3.05 times 10 to the 22 molecules. And that's problem number 5. Problem number 6. What is the mass of a 300 milliliter sample? So that's our volume. We're going to change that to 0.300 liters. Just going to move our decimal point back 3 places. Here we see a pressure of 2 atmospheres, a temperature, add 273, so that's going to be 303 Kelvin. And what is the mass of that sample? So mass is going to be grams, and we know that this is hydrogen chloride, HCl. Well, again, if we knew the moles, then we could figure out the grams. So it's going to be a 2-step problem. So let's start off with PV equals nRT. N equals PV over RT. I'm going to be a little tight on space, so I'm going to leave off my units this time. So my pressure is 2 atmospheres. My volume is 0.3 liters. My value of R, since I'm using atmospheres, is 0.0821. And my temperature 303 Kelvin. When I do all of this, I get a value of 0.0241 moles. Now we want grams out of this, so we just have to know that 1 mole of HCl, chlorine is 35.45, hydrogen's 1.01, so it'll be 36.45 grams, which gives us a value of 0.879 grams HCl. Now, what is the density of this sample? Okay, density we know is mass over volume, DMV. And we're given that the mass is 0.879. We just figured that out. And the volume we know is 0.3 liters. So all we have to do is divide those two, and we get a value of 2.93 grams per liter. And that's the gaseous density. Problem 7. A 30-gram sample of methane occupies 150 milliliters at 0 Celsius. What is the pressure? Okay, so we're looking for pressure. We know that the temperature is 273 Kelvin. We don't want to use 150. We're going to say the volume is 0.150 liters. And we don't really have moles, but we can figure out moles because we have 30 grams of methane. Because we know the formula, we can say 1 mole of methane, carbon is 12.01, each hydrogen is 1.01, so we know that that's 16.05 grams. And when we use that value, we get 1.87 moles of methane, and that's our N. So now we're just going to go back and do the problem. So PV equals nRT. We're looking for the pressure. So pressure equals nRT over V. Moles, 1.87 moles. Okay, the value R. R, the pressure, again, is doesn't state what unit. So if we use 0.0821 liters atmospheres per mole Kelvin, then our answer will be in atmospheres. The temperature 273 Kelvin, and the volume is 0.150 liters. When we get all done, we get a value here of 279 atmospheres. And that's problem 7. Problem 8. What volume in liters does an 85-gram sample of CO2 occupy at 1.4 atmospheres and 80 degrees, which before we have a chance we're going to change that to 353 Kelvin. And again, here we have an 85-gram sample of CO2. We can use that information to figure out how many moles there is. So the moles is 85.0 grams. Okay, carbon is 12.01, each oxygen is 16, so that's 44.01 grams for 1 mole of CO2. So when we calculate that, we get something a little bit more than 2, and that comes out to, a little bit less than 2, 1.93 moles. So we are looking for the volume. So PV equals nRT. So we want volume, so volume is nRT over P. And again, because I'm tight on room, I'm going to just use the numbers. 1.93 moles. We're using atmospheres, so we use 0.0821 as our value for R. Temperature is 353 Kelvin. And the pressure is 1.40 atmospheres. So when we get all done and do all our math, we get that this volume here is 40 liters. Now, what's the density of this gas? Again, density is mass over volume. We know that the mass is 85 grams. We know our volume is 40 liters. So we can see we're going to get about 2, so 2.13 grams per liter as our density. Number 9, how many moles of an unknown diatomic gas are contained in 500 milliliters? So that's a volume, and we're going to make that 0.5 liters at 1.2 atmospheres, 25 degrees. That's our temperature. We'll make that 298 Kelvin. And how many moles? We're looking for N. So we have PV equals nRT. N equals PV over RT. Pressure is 1.2 atmospheres. Volume is 0.5 liters. R, because we're using atmospheres, R is 0.0821. And temperature 298 Kelvin. Taking out the calculator, we're going to find out that is 0.0245 moles. That's the first part of the problem. Now it says if this unknown diatomic gas has a mass of 0.93 grams, what's the molar mass and what's the gas? Well, the diatomic gases, could be something like nitrogen that weighs 14, but diatomically it'd be 28. Could be oxygen, could be fluorine, could be chlorine. Those are diatomic. The other one it could be would be hydrogen, if it comes out to be about 2. So let's see what happens. Here we have 0.93 grams, and this is 0.0245 moles. And if we divide our grams by our moles, we get a value of 38.0 grams per mole. So that's going to be double something. Certainly not hydrogen. Oxygen doesn't sound right. Because oxygen, that would have been 32. This would have been 28. This would have been 2. Fluorine is 18.998. Double, that's about 19. 19 times 2 would be about 38. So that is it. So we're talking about a sample of fluorine gas. Chlorine would have been about 71. So, what's the molar mass of the gas? And what gas is this? This must be fluorine gas. Diatomic. And that's how we do ideal gas law problems.